Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 32 of this course on machine learning for earth system sciences. We are in module 4 where we are discussing like how machine learning can be used for earth observation systems, and in the topic of this lecture is precipitation nowcasting from remote sensing. So nowcasting is a concept which we have discussed briefly earlier also for extreme weather nowcasting and so on. So here the input sequence will be some kind of a spatiotemporal like a spatiotemporal sequence, and the input is that, and the output which we are trying to forecast is also a spatiotemporal sequence. However, in this case the predictor variables, like they will be presented as some kind of like as a instead of having actual measurements of these predictor variables, we will be having maps obtained from the remote sensing. And as we have discussed in the just the previous lecture, that these remote sensing like they can act as proxy for different these meteorological variables. They may not be directly measured by the remote sensing imagery, but the remote sensing imagery can act as a proxy for all those variables. So in this work, we like in this lecture, the research papers that we are going to discuss, they do not specifically measure those variables, rather they use the like the remote sensing images, especially the radar images, like directly, on which they apply the machine learning algorithm. The covariate information, we can say, we can like look at it in this way, that covariate information is implicit in the form of some proxies in the neural network, but they are never brought out explicitly, but rather it's directly fed into the machine learning or deep learning model, which brings out which maps the those remote sensing imagery to the quantity of interest, which in this case is rainfall. And so like we will see different models, machine learning models for this purpose. We will see convolutional LSTM, which we have discussed like briefly in earlier also, and we will also see GRUs or gated recurrent units for the sequence modeling. So now coming to nowcasting of precipitation, as has been already discussed. So this is basically for doing the forecasting at a short duration, typically a few hours. And however, in this case, unlike some of the other nowcasting applications which we may have considered, in this case we need a spatial map of the target variable. That is, at every location I should be able to make an estimate of how much rainfall is going to happen after say 5 hours or something like that. So the input in this case is a remote sensing imagery which acts as a proxy of different variables, including maybe the target variable, that is the rainfall. So like when we are obtaining the radar imagery at this point of time, like the pixel intensities at for corresponding to different locations, they may have different they may be encoding different information, including the how much precipitation is happening right now, and the aim is based on this to construct the precipitation map for the maybe 5 hours in advance and so on. So the target is to develop a like a map of the input, is to develop something like a map sequence of the target variable, in this case rainfall. So like what we are trying to do is to build a mapping of, like you can say, a mapping of maps. The input is like the radar imagery, which is like a proxy for a map of different variables, and the output is also going to be a map of the target variable rainfall. And not only that, the input is a sequence of maps, the output is also going to be a sequence of maps. And for this purpose we are going to consider different kinds of sequential neural networks which have the spatial which are suitable for spatial input and output. So the first model which we are going to consider for this purpose is conv LSTM, which we have mentioned a couple of times in our previous lectures also. The goal of precipitation nowcasting is to predict the future rainfall intensity in a local region over a relatively short period of time. A few previous studies have examined this crucial and challenging weather forecasting problem from the machine learning perspective. In this paper, we formulate precipitation nowcasting as a spatiotemporal sequence forecasting problem in which both the input and the prediction target are spatiotemporal sequences. By extending the fully connected LSTM to have convolutional structures in both the input to state and state to state transitions, we propose the conv LSTM and use it to build an end-to-end trainable model for the precipitation nowcasting problem. Experiments show that our conv LSTM network captures spatiotemporal correlations better and consistently outperforms FC LSTM and the state-of-the-art operational rover algorithm for precipitation nowcasting. So this is what the conv LSTM looks like. This, I think we have these figures we may have seen earlier also. So first of all, this is the standard LSTM, as mentioned earlier. So it has this hidden state and it has the cell state, which represent the long term and the short term and long term memories respectively. Based on the input xt at every given state, like the ht, the short term memory is updated and the cell state can also be updated. So there is internally a signal called forget is generated based on the input and the current memory storage. So if the forget input is activated, then the cell state is reset, that is the long term information that is present gets erased and new information gets stored in it for preserving for the next steps and so on. And these ht, the hidden state the variables, these contain the short term memory, the short term memory which is updated at every given step as the input comes in, and we can have the output also at every given step. Now so that is what a convolutional unit looks an LSTM unit looks like. Now to increase the representative power to have a longer long term memory and so on, it's we often use stacked LSTM units. That is, instead of having a single LSTM unit, we just connect several LSTM units in parallel and so on. And then so here is the input is now in this case the input is not a ordinary sequence, but a sequence of we can say a spatial map, which is effectively an image. And we know that whenever the input has some kind of a spatial structure, as in a 2D or 3D spatial structure as happens in an image, then the normal fully connected approach, which is which can be represented in a neural network by these these weight multiplications and so on, but this does not work very suitably. Rather, convolution is a more useful feature, is a more useful approach, because it is capable of representing the repetitive nature which is present in an image. So in this case, what happens is that these matrix multiplication operations and so on, which are present in a usual LSTM, these are actually replaced by convolution operation. And so the input, this x, instead of being a vector or a matrix, now becomes like a spatial map on which this kind of convolution operation takes place, and these w's, instead of these being ordinary weight matrices, these are now turned into convolutional kernels. So the way the whole thing works is as follows: we have an input sequence. Input sequence is fed to this convolutional LSTM one step at a time. Because it's a sequence of images, at every point of time one image or one spatial map is fed into the LSTM, and the LSTM at each step creates some kind of an intermediate representation by passing it through the all the stack layers, and in the different like in the successive steps this it's updated also, I mean both the long term as well as the short term memories. And like now finally when the entire input is fed into the LSTM, it generates something like an intermediate representation. Now that intermediate representation is then used for the forecasting purpose, that is there is a decoder network which creates the output sequence from that intermediate representation. So like there is an encoding step and a decoding or the forecasting step. So the this encoding is one set of convolutional LSTMs, and this output the G forecasting, which they have like as mentioned in this paper, that is also like a conv LSTM or stacked conv LSTM. The reason why both input like I mean the output also needs to be a conv LSTM because the output is also going to be a spatial map or an image just like the input. So the data set they have used for this study is like radar echo data over Hong Kong from 2011 to 2013. So this is a 2-year period, but within that they have focused on only 97 rainy days because that is when the observations were available. So the radar of course measures its like it's the reflectivity it measures. So from the radar images the intensity values, first of all the intensity values are like normalized using this kind of an operation. So and then projected to the range 0 to 255 as happens in an ordinary image. Also these radar maps are cropped so that they focus on the particular region of their interest. Now these radar maps are acquired every 6 minutes, that is there we get 240 frames every day. And now for the purpose of training the network, what they have done is each of these daily sequence of these 240 frames they divide into 6 non-overlapping blocks. So if 240 frames are divided into 6 blocks, so there will obviously be 40 frames in each block. Now for every day we get 6 blocks like this. 4 of these blocks are used for training, 1 for validation and 1 for testing. And so like this is the conv LSTM model so they use this for the rainfall prediction purposes as mentioned. So they like whenever there is nowcasting, then we have these standard indices for nowcasting, which we have discussed earlier also for the lightning nowcasting case. So there is the POD or the probability of detection, the FAR false alarm rate, the correlation coefficient is of course there, and so on. So they compare the proposed conv LSTM architecture with a fully connected LSTM in which the input is not provided in the form of this kind of a spatial map, but is simply vectorized. And then there are these various rover algorithms. These rover like this is simply based on the notion of optical flow. So this is optical flow is a concept in computer vision or machine learning. Like basically it's used for something like as video prediction. So suppose you have a video is nothing but a sequence of images in which across which there is some motion, say the video of a car running or something like that. So between the frames there is going to be some small motion, the objects will have shifted a little bit from one side to another and so on. So like basically what optical flow does is like at every pixel it measures the shift that may have happened from the previous frame to the current frame, and that same shift it tries to extrapolate to predict what the next frames are going to be. So these so based on this concept of optical flow, there are some rover algorithms which are used for these radar sequence mapping. That is they imagine the radar image sequence as something like a video, and based on that they try to like predict the future radar sequences. Now these from the radar sequences there is some Marshall's algorithm by which it's actually possible to map the radar inputs to rainfall. So that is some kind of a parametric relationship that some meteorologists have come up with. So using that they try to predict the rainfall. So it's a two-step process. First you forecast the coming the future radar maps, and based on that you by using the parametric formula you calculate how much rainfall can happen in the coming points of times. So they have compared these approaches, and they find that conv LSTM performs the best not only over the rovers but also over the fully connected LSTM, which emphasizes the fact that using this convolutional operation here is very crucial. Now building on this conv LSTM model, another paper appeared by the same group of authors, Shi et al. They propose another model which they show to be even better than conv LSTM. With the goal of making high resolution forecasts of regional rainfall, precipitation nowcasting has become an important and fundamental technology underlying various public services ranging from rainstorm warnings to flight safety. Recently, the conv LSTM model has been shown to outperform traditional optical flow based methods for precipitation nowcasting, suggesting that deep learning models have a huge potential for solving the problem. However, the convolutional recurrence structure in conv LSTM based models is location invariant, while natural motion and transformation such as rotation are location variant in general. That is to say, from one that is when we are considering a convolutional operation, so it's like the same convolution kernel is used all over the image and so on, but what they are saying is that the if instead of doing that, if we could somehow differentiate between different different locations, how the convolution will take place, or how the basically how the recurrent structure will take place in different parts of the input, that might be useful. So that is here basically they are trying to focus on the nature of the trajectory, the trajectory means at the path over time taken at different locations. So that might be different from one location to another, and it is this trajectory that they are trying to somehow focus on and model it in this work. Furthermore, since deep learning based precipitation nowcasting is a newly emerging area, a clear evaluation protocols have not been established. To address these problems, we propose both a new model and a benchmark for precipitation nowcasting. Specifically, we go beyond convolutional LSTM and propose trajectory GRU or TRAJ GRU model that can actively learn the location variant structure for recurrent connections. Besides, we provide a benchmark that includes real world large scale dataset from the Hong Kong Observatory, a new training loss, and a comprehensive evaluation protocol to facilitate future research and gauge the state of the art. So in this work, of course, in this lecture we will focus only on the TRAJ GRU model, but this paper also provides a benchmark dataset and a way to evaluate this kind of a radar based or satellite based forecasting of rainfall. We will not go into that, but I leave it as a homework for you to work on. So this is what the general structure. The general structure is more or less unchanged compared to the the conv LSTM. So the at any given point of time, the inputs are presented in the form of the spatial maps or the radar images in this case. So the it undergoes a sequence of convolutions and RNNs and so on. So we see the multiple the RNNs, these might be LSTMs or LSTMs or other sequential units which are used in machine learning, such as GRU, graded recurrent units. So I will explain to you in a bit what this GRU is all about. But as you can see that there are multiple stacks of RNNs. So first the image undergoes one round of convolution, then there is a RNN, that is basically there is this hidden variable which is updated, then there is another round of downsampling followed by again an RNN, this is the second level of the hidden variable, then there is a further downsampling and then again RNN and so on, and these the hidden variables, these are updated and passed on to the next step, where again a new input comes in and undergoes all the convolution and downscaling steps, and they are further used to update the memory through the RNNs and so on. So this way the whole encoding process goes on. The entire like input sequence is encoded just as already discussed, and then there is the forecaster which does the forecasting. Now these RNNs can be LSTMs, they can be or they can be GRUs and so on. So now in the convolution, as they are saying, that in the convolutional RNNs the recurrent connections are fixed over times, but they are like in what they are proposing right now is the trajectory RNN, where the recurrent connections are dynamically determined. That is, it's not like when in the conv LSTM it's like the same thing which is being used all the time, but in like what they are calling it as traj GRU, like as you can see, these connection structure, this has changed, and like this is like this changes from one input point, like at t equal to 1 it is something, at t equal to 2 it will be something else, and so on. And these the changes which they are talking about, this will not be like, it's not that these changes are going to be random, but it will depend on the current state, I mean the current memory state and so on. So and now that brings us to the concept of GRU. It's a gated recurrent unit. Like you can say it's a smaller scale version of an LSTM, but like it has slightly less number of operations as an LSTM. So like it does not have an LSTM has this cell state which is the long term memory, and the usual hidden state which is the short term memory, which is also used in RNNs. At every point of time there is a forget signal is generated in the LSTM, which indicates whether the cell state has to be reset or not. But in case of GRUs, there is no separate cell state, nor is there any forget gate. Instead, there is an update signal which indicates that the memory by how much it should be updated. That is, the memory now, the single memory now acts as part of like it's a combination of long term and short term memories. The thing is, it is neither like fully updated, like it's not fully updated as happens in case of RNN, nor like in LSTM, but rather the update signal indicates how much of it has to be updated and how much of it needs to be like preserved for the coming steps. So like this is slightly less expressive as suggested. Like in case of LSTM, the two things, the long term and short term, are clearly delineated so that it will be more expressive. In this case it's not that. So the short term memory itself is trying to, you can say, accommodate a part of the long term memory, so it will be less expressive, but it is faster. So this is what the GRU, so like based on that they have proposed two variations. One is the conv GRU and the traj GRU. So in case of the conv GRU, this is just like the usual GRU, where these stars are all the operations. Now in a normal GRU, these operations are the usual matrix multiplications and so on, where these W's, X, Z, etc. these are like you can say that these are full weight matrices indicating fully connected neural network layers. And so so first an update signal is generated, a reset signal is generated, and the new memory value H is generated based on the current input as well as the past memory and the reset. So like this reset indicates whether the past memory that should be should be forgotten or not, and also the ZT is the update signal which we mentioned earlier. So accordingly that is, if this ZT is this will be a binary variable, either 1 or 0, and so if ZT is equal to 1, that means the memory will not be updated. That is basically the current value of the memory will continue to be present. But if ZT is equal to 0, that means whatever new information has been created, that information will now be will be stored in the memory, and the old information will be deleted. So this is how the conv GRU works. So the conv GRU GRU simply replaces these fully connected layers by a convolutional layer. So these matrix multiplications are replaced by the convolution operation, and these WXR, these matrices, these basically now get replaced by convolutional filters. So that is the conv GRU. So this is conv GRU. As you can see, is a like a direct analogy of conv LSTM. The alternative is to have traj GRU, in which, as they have mentioned earlier also, all these recurrent corrections, they like vary from every point of time. So that is achieved by these two intermediate variables ut and vt. So based on the current input and the past memory, as a function of that, these two signals ut and vt are generated, and these ut and vt, these are used to warp the past memory, the ht minus 1. So like this warping of the ht minus 1, this basically helps to change the recurrent structures, as they are saying. Now this warping does not happen like randomly, but as a there is this function gamma of the which takes the xt and the present input and the past memory, and does some kind of operation on it. And now like in case of conv LSTM, this gamma, this is like it's some kind of a constant function, but in the traj GRU, this like it's not constant. It's some like it's a function that changes its value, and these so like basically the like if you look at the h prime, which is the new information generated at every point of time, it's so like it takes into account the neighboring structure of every I comma j, that is so this h is now something like a special map where like there are these locations. So these so every location has its neighboring location. So like all these parameters of the neighboring locations are warped, as this operation indicates, and based on that the new information is generated. So now coming to the traj GRU nowcasting experiment. So the data set like it's an upscaled version of the previous radar echo data set that was used for conv LSTM. So this is used for the period 2009 to 2015 over Hong Kong, and now there are as you can see this has been scaled up. So instead of 97, there are now 812 rainy days which are available for training, 50 for validations, and 131 for scaling. So these are the radar reflectivity images. Their resolution is 480 by 480. They are taken at an altitude of 2 kilometers, and they cover this kind of this 512 cross 512 kilometer areas over the over the region of Hong Kong. So at every kilometer wise, like it's the aim is to like make the forecasting. And so that there is a pre-processing step also, where these raw radar reflectivity images, they are transformed to the pixel values by according to a formula like this, and they are also clipped to the region 0 to 255, so that it becomes effectively an RGB image in the a grayscale image in the visible spectrum, on which all these convolution etc. operations can be done easily. And so these are some of the results. So like they instead of forecasting the exact amount of rainfall, they basically do some kind of binning. The rain rate is divided into several bins like this, and at every bin they try, like bin wise, they try to make the prediction, and they show that for almost all the bins, like say the bins means like very little or hardly noticeable rainfall, light rainfall, or light to moderate rainfall. So like when they are forecasting the rainfall, rather than they effectively forecast that these are the bins of rainfall that are going to happen after say 4 hours or something like that, and they show that for all the bins the traj GRU is giving a better result compared to all the existing methods, including like conv LSTM as well as conv GRU. Okay. So now we will just briefly discuss one more paper. Here the target is precipitation nowcasting with from satellite, or in fact radar imagery, but here the aim is, rather than focusing on a fixed region like Hong Kong, they are trying to build a worldwide map of precipitation in the like based on the satellite and radar imagery. Now it might happen that in some regions the radar network is strong, so that they have better data. In other places they may not have so much data. So like in these, especially in this work, they have a good radar network in this entire Russian region, which provides them a good source of data. In the other parts of the world, they have to depend on the satellite imagery to make the predictions, and along with it, they also use the simulations from a numerical weather prediction model, which is the GFS, and using that they make the like the estimation of the precipitation over all over the world. So in this case, the primary source of information is the of high resolution precipitation is obtained from the network of the ground based radars. So it's basically C-band Doppler effect radars that measure the reflectivity and radial velocity of raindrops in the atmosphere. The observation field in this case is a circular area of a radius of up to 250 kilometers around the radar's position. So the echo which is obtained by the radar, which is like basically the measurements of the radar, they can be converted to the precipitation. Like in the previous case also I had mentioned this, that there is a parametric formula called the Marshall-Palmer formula, which is useful for like mapping the radar's value, the radar observations to the rainfall values. So like and it is like these rainfall values are obtained at very high spatial resolution, as you can see 2 kilometers by 2 kilometers at a temporal resolution of 10 minutes. So like this is basically a two-step process which they have followed in this paper. So the first step is the extrapolation of the radar observation. So like this is done using the optical flow, which that also we mentioned in the context of the rover algorithm earlier. And the step 2 is the rainfall field in the spatially shifted direction of wind using the Cornwell STM. So first of all, there is they estimate the wind, then they use the common sense that from the current time to the next time where they are going to make the prediction, by the rainfall is likely to have shifted in the direction of the wind, and this wind direction is of course different in different parts of the world, because in this case they are making a worldwide forecast of rainfall. So this is obtained. So basically they get the wind direction map all over the world using the optical flow. Then the current rainfall map that is shifted according to the rainfall in the next map, and for this shifting purpose they use take the help of Cornwell STM. And also the numerical weather forecast using a model known as GFS. So like we have already discussed about the numerical weather prediction models in the context of the LightNet. So these models are also used as additional inputs. And so this is how the model they have developed is effectively the UNet, which we have discussed several times earlier. And so like they have the UNet which may or may not be accompanied by the input from the GFS, which is the numerical weather prediction model. Apart from that, like they have compared it with various baselines. So PP and MPE are some physics based algorithms. So these are like purely like you can say numerical weather models which are not based on machine learning. And then there is the pointwise approach, where there is a neural network with two convolutional layers. It's like but applied to every location individually. So like without taking the neighborhood effects, which is done in the case of like a model like UNet and so on. Also in case of the UNet architecture, so like the convolution in this it is used the convolution operations, they are used to take the spatial effects into account and so on. And in the like as these results suggest that this UNet with GFS that often performs the best. So in UNet without GFS can also do well in certain situations, but in general the proposed UNet model along with the numerical weather prediction that gives the best results. And these are like some of the results in different period in different parts of the world, because they have done the worldwide estimation, and they have also done it in different months. So in different months also they have plotted the results and so on. So these are the 3 papers that we discussed, and that brings us to the end of this lecture. So we the basic points to remember is that when we are trying to estimate the spatial field of a particular variable, we are trying to predict a spatial map of I mean, we focused on precipitation, but it can be done for other variables also potentially. So like in that case, it is important to incorporate a convolutional component into your machine learning model, and if you want to do the sequential prediction, you also need to have a sequential model, be that LSTM or GRU or something like that. And it is possible to, but also the input for the input you need not have actual measurements of the different variables, but rather the radar or satellite measurements themselves can provide as suitable inputs. For the neural networks have sufficient representative power that will be able to map the radar inputs to produce like a map of the variable which is of your interest. So that brings us to the end of this lecture. In the next lecture 2, we will discuss some some aspects of how machine learning can be used in remote sensing and earth observations. So till then,